Hello students, this is Professor Waite pre-recording the lecture for you. The lecture date is August 29th, 2017, and it will be lecture 3. You should have turned in your homework using the portal on Blackboard. If you have any problems or issues with that, please send me an email. The next homework will be due Tuesday, September 5th, and again you can see Blackboard for that handout and also submit it on Blackboard as well. Today we're covering chapters 6 and 7, which is a review from the previous semester. We're going to talk about reversible and irreversible systems, heat engines, refrigerators, and heat pumps, and then we're going to go into an in-depth discussion of chapter 7, which is all about entropy, culminating in an entropy balance. A thermal reservoir is a theoretical body with a large thermal energy capacity. So this is talking about something that can absorb or release finite amounts of energy without undergoing a temperature change itself. And a source is a reservoir that will supply energy to our system, so the temperature of the reservoir is greater than the temperature of the system. And a sink is a reservoir that absorbs energy, so the temperature of the reservoir is less than that of the system. So we need to look at these reservoirs, try to determine what temperature range is suitable for our application, but then we also need to properly manage them because thermal pollution is an issue that we have to consider whenever we are dealing with an environmental reservoir like a lake or a river or even just the air. Some sources might include furnaces, boilers like we would find in a steam power plant. We can use geothermal energy, which is energy absorbed from the heat in the ground. Solar energy, and in many cases, waste heat from other processes can be used as a source. Then our thermal sinks might be lakes, rivers, oceans, the ground, the air, and this is where we really need to consider the thermal pollution or other considerations as we use our environment around us as a sink or, in some cases, a source. A heat engine is a device or a system that receives heat from a high temperature source, converts part of this heat to work, and then rejects heat to a low temperature sink. And heat engines operate on a cycle so that you can have a network output at every phase of the cycle. Usually there's some working fluid to and from which the heat is transferred. So perhaps you have a steam engine or you're using some refrigerant type coolant or fluid that can absorb and release certain amounts of heat given the temperature of the reservoir. The steam power plant is the quintessential example of a heat engine. The energy source might be a furnace, such as that is coal-fired or natural gas-powered, and we receive heat into the boiler at this point, Q in. That steam is then run through a turbine, which generates a network output. And as it runs through the turbine, the temperature of the steam decreases and also the pressure decreases such that the outlet of the turbine is usually a saturated liquid or very close to a saturated liquid, or saturated vapor, pardon me, or very close to a saturated vapor. We don't want liquid coming out of our turbines if we can help it. This is then run through a condenser, which condenses this liquid vapor mixture or this vapor to a liquid which is pumped back up to the boiler to heat it again. So during this condensation process, some of the energy from the liquid is removed and deposited in an energy sink. And in many cases, this is just the atmosphere, the air around us. So if we want to look at the network output of this entire cycle, it's just the amount of work we get out of the turbine minus the amount of work we put into the pump. Or we can look at it in terms of the thermal properties, so it's Q in minus Q out. The thermal efficiency is the fraction of our heat input that is converted to work. So if we look again at this steam power plant, we have a heat input, Q in. A portion of that is converted to work at work out, and some of that heat is then deposited into the atmosphere. So our thermal efficiency is defined as the work net out over Q in, or we can substitute work net out as Q in minus Q out and rearrange the equation in terms of the heat transfer only. The thermal efficiency of a heat engine will always be less than 100%, and it's usually on the order of 60%. That would be a really good heat engine if it had a thermal efficiency of 60%. This is defined by the second law of thermodynamics, which we'll talk about in a minute. Refrigerators operate in a similar fashion in that they're operating on a cycle with a condenser and an evaporator. However, refrigerators require a network input in order to transfer heat from a cold space to a warmer space. So we talked previously about the warm coffee cup on the counter, where this coffee cup can't spontaneously absorb heat from its environment to get hotter when the environment is cooler than the coffee cup itself. However, with a refrigerator, we can use a network input to reverse the natural flow of heat and actually add heat from a cold space to a warmer space. So Q sub L is the heat removed from this refrigerated space at T sub L. Q sub H is the heat rejected to the kitchen environment at a temperature T sub H. And then the network input is the work required to operate the compressor. And in this case, if we use an expansion valve in order to exact a pressure and a temperature drop through the system, then really we only have to put work into the compressor. We don't have an additional steady flow device that requires any kind of a work input. So when we look at refrigerators, we want to know how effective they are and to be able to compare one system to another. And we do that by calculating the coefficient of performance, which in this case is our desired output over our required input. So our desired output for a refrigerator is to make a cold space colder, or in other words, Q sub L. We're removing heat from Q sub L. The required input is the work net in to the compressor. So our coefficient of performance is just Q sub L over work net in, which we can rewrite as Q sub L over QH minus QL, or 1 over QH over QL minus 1. So a couple of different ways to rewrite that. A heat pump is very similar, except for in this case, we're not trying to make a cold space colder. We're trying to make a warm space warmer. So Q sub H is the heat added to the indoor space at temperature T sub H. Q sub L is the heat extracted from the outdoors at T sub L. And then this network input is the amount of work required to operate the compressor. So again, our coefficient of performance is our desired output, which is adding heat to a warm space, Q sub H, divided by our required input, which is the work net in to the compressor. And again, we can rearrange those factors and we can calculate our coefficient of performance for a heat pump and our coefficient of performance for a refrigerator. And you notice that the coefficient of performance for a heat pump is always going to be greater than that of a refrigerator, because we have some net added benefit as we put work into our system. That work can be partially converted to heat, add additional heat to the indoors. A heat pump operates the same as a refrigerator, but the desired output is different. Okay, so a heat pump, we desire for the warm space to get warmer, whereas a refrigerator, we want the cold space to get colder. And most heat pumps, especially in this area of the country, are reversible, so they can operate as a heater in the winter and as an air conditioner in the summer. And the coefficient of performance of a heat pump will always be greater than that of a refrigerator when we're considering it having identical components. So let's do an example of this. In this example, we have a home heating and cooling system which uses the same unit to heat a home in the winter and provide air conditioning in the summer. If the system requires a power input of 30 kilowatts to the compressor and extracts heat at a rate of 40 kilowatts from the cold temperature space, compare the COP when operating as a heater versus operating as an air conditioner. Okay, so the first thing we need to do to set up this problem is really to draw a picture so that we can understand it. So if we look at a heat pump versus a refrigerator, we notice a couple of different things. First of all, the heat pump is adding heat to the home, whereas the refrigerator is removing heat from the home. We're told that the power input to the compressor is 30 kilowatts. So that will be this arrow here, the same for both systems. However, it extracts heat at a rate of 40 kilowatts from the cold temperature space. So in the case of the heat pump, this 40 kilowatts comes from the outdoor air and then is added to the house. So this is the 40 kilowatt term, this arrow. Whereas the refrigerator, the 40 kilowatt term is this arrow here. So 40 kilowatts is removed from the home. Okay, so it's trying to cool the home and heat is removed at a rate of 40 kilowatts, whereas in this case, heat is extracted from the environment at a rate of 40 kilowatts. So let's look at this example in PDF form. So you can see I've drawn simplified versions of those pictures. I've labeled everything, so I have a Q sub L, I have a Q sub H for both systems, and then in the case of the heat pump, my home is at T sub H, and in the case of the refrigerator, my home is at T sub L. So the coefficient of performance for both cases is the desired outcome over the required input. So let's first look at the coefficient of performance for the heat pump. So in the case of the heat pump, our desired outcome is to add heat to a warm space to make it warmer. And our required input is this 30 kilowatts. Okay, we're given Q sub L and work dot in, but we're not given Q dot H. However, we can figure from this diagram and from our knowledge of heat pumps that Q dot H will be equal to work dot in plus Q dot L. So we can write our coefficient of performance for the heat pump as Q dot H over work dot in, which is equivalent to work in plus Q dot L over work dot in. So if we plug in the numbers for that, we get 30 kilowatts plus 40 kilowatts. So that's our work in plus Q dot L divided by 30 kilowatts is equal to 2.333. So that's the coefficient of performance for the heat pump. Now looking at the refrigerator, we perform a similar analysis. In this case, our desired outcome is to remove heat from a cold space and the rate of 40 kilowatts using a work input or required input of 30 kilowatts. So our analysis gives us a coefficient of performance for the refrigerator is equal to Q dot L over work dot in, which is just 40 kilowatts over 30 kilowatts, or in other words, 1.333. And you can see that the coefficient of performance for the heat pump is exactly the coefficient of performance for the refrigerator plus 1. Okay, so this heat pump will have a greater coefficient of performance for the same rate of heat transfer, the same components to the system and the same requirements. It will operate with a greater effectiveness to add heat to a warm environment, which is less difficult than removing heat from a cold environment. Heat engines are work-producing devices, and refrigerators and heat pumps are work-consuming devices. So it's not possible to obtain a greater amount of work output than heat input. However, it is possible to obtain a greater amount of heat output than work input, as we see in the case with the heat pump and the refrigerator, that because we're adding energy to the system in the form of work, and we're also extracting energy from the environment, we can actually add more energy to our home than by just simply using a resistance heater to heat up our space. So when we compare the cycles, we can see that the thermal efficiency, the coefficient of performance, are calculated slightly differently. However, they follow a similar methodology in that we look at the required input over our desired output over our required input. The Kelvin-Planck statement is a statement of the second law of thermodynamics, so it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So this is an impossible system that we're seeing here. So in other words, heat engines can never be 100% efficient. The Clausius statement is also a statement of the second law, in that it's impossible to construct a device that operates and produces no net effect other than to transfer heat from a lower temperature body to a higher temperature body without a work input. So as we know, work is required in order to reverse the flow of heat. So to transfer heat from cold to warm, we have to put work into the system. And so through the magic of thermodynamics and using a cycle with a working fluid, we can do that. However, it requires adding work to our system. A reversible process will provide the best case scenario for any process. So it will be the greatest amount of work produced or the least amount of work consumed for any process. And so although these are the theoretical limits of this system, we still like to study them because, one, they're easier to study, and two, it allows us to look at the best case scenario. So we can't ever achieve a fully reversible process, but we can get close. And it also provides just that benchmark or that bound against which we compare our real systems. Irreversibilities that come into play are often friction or unrestrained expansion, electrical resistance. So some of that work we put into the system is converted to heat. This is often a desirable quality if our objective is actually to create heat, but in some cases it's a loss. Heat transfer is always a one-way process, so unless there's work involved, we can't regain that heat that we've moved to a different place. Anytime we mix fluids, it's combined into a mixed media. We can't separate that out without having to do work. Chemical reactions is the same thing, so there's some energy released during that reaction that can never be recovered. And then inelastic deformation, because there's work required to return it back to its original shape. And in some cases, it can never be returned back to its original shape, like maybe the fender that gets crunched on a car. So let's talk about one of the more famous reversible cycles, and that is the Carnot cycle, where we have reversible isothermal expansion from state 1 to 2. So we add heat from a source at TH to maintain a temperature during an expansion process. So if we were to just expand without adding heat, the temperature would tend to decrease. However, we add heat to maintain the temperature at T sub H. Then we have a reversible adiabatic expansion. So now we don't allow any more heat transfer to occur, and the cylinder is insulated. So as we expand, our temperature decreases from T sub H to T sub L. Then we have a reversible isothermal compression. So as we're compressing this working fluid, heat is removed so that the cylinder maintains the temperature T sub L, and the heat, that waste heat, is deposited to a sink at T sub L. And then lastly, we have reversible adiabatic compression. So we insulate our cylinder and we compress it further without any heat transfer, so our temperature would necessarily increase back up to TH. So then we would repeat the cycle again from states 1 through 4. So you can see this process on a PV diagram, that the Carnot cycle operates as such. And we can also operate the reverse Carnot cycle, where in this case, the Carnot cycle is representative of a heat engine, and the reverse Carnot cycle is representative of a heat pump or refrigerator, depending on which side we are more concerned about, whether we're more concerned about removing heat or more concerned about adding heat. And the Carnot principles are that the efficiency of any irreversible heat engine is always going to be less than the efficiency of a reversible heat engine operating between the same two temperature limits or the same two thermal reservoirs. And then we can also say that the efficiencies of all reversible heat engines operating between these same two temperature limits is going to be the same. So the Carnot cycle provides the absolute best case scenario for any cycle, reversible or irreversible, when we consider these temperature limits. So the Carnot heat engine, as I mentioned, operates on the Carnot cycle, and we can calculate the efficiency by substituting T sub L and T sub H in for Q sub L and Q sub H. And again, this is the highest possible efficiency of any heat engine that operates between those two temperature limits. So, and bear in mind and keep note that T sub H and T sub L are always in Kelvin or Rankine as we calculate this thermal efficiency. You have to use absolute temperature or thermodynamic temperature scales. So let's do an example of the Carnot heat engine. If we have a heat engine receiving 650 kilojoules of heat from a source of unknown temperature and rejecting that heat in rejecting 250 kilojoules of that heat to a sink at 24 degrees Celsius. We want to determine A, the temperature of this source, and then B, the thermal efficiency of our heat engine. So let's look at that example on this next page. Okay, so we have this Carnot heat engine, and we can simplify it a little bit and add some subscripts and values to our drawing. So we have this thermal reservoir T sub L, which is at 24 degrees Celsius. That's a degrees Celsius there. Sorry, it's a little hard to read. And I converted that to Kelvin because I know when I'm working with thermal efficiencies that I want to work in terms of Kelvin. We learned that it receives 650 kilojoules of heat and rejects 250 kilojoules of that heat to the sink at 24 degrees Celsius. Okay, so in order to determine our thermal efficiency and our the temperatures of the source, we need to use the relationships that are valid specifically for the Carnot heat engine. So the efficiency of a reversible heat engine is equal to the efficiency of a regular heat engine. So we can say that 1 minus Q sub L over Q sub H will be equivalent to 1 minus T sub L over T sub H. And in other words, if we drop the 1, then Q sub L over Q sub H, that ratio of heat will be equal to T sub L over T sub H. So we can rearrange and solve for T sub H, and we get T sub H is equal to T sub L times QH over QL, which if we put in the numbers for that, we have 297 Kelvin multiplied by 650 kilojoules over 250 kilojoules. So again, working in Kelvin is important. So we find that that thermal reservoir has a temperature of 772.2 Kelvin, which if we convert to Celsius is just 499.2 Celsius. We can then use that value back into our original equation, 1 minus TL over TH, and substituting in, again, in terms of Kelvin, this is 297 over 772.2 Kelvin, we get a unitless answer, and if we multiply by 100, we get a thermal efficiency of 61.5%. So you can see that for this heat engine, it has a thermal efficiency around 60%-ish, and it's a reversible heat engine. It's the best possible case. So any real heat engine would have to have an efficiency of less than that number. Okay, so as we talk about reversible, irreversible efficiencies, it leads us necessarily to the discussion of entropy. So if you remember from last semester, entropy is just disorganized energy. And when we have energy that's disorganized, we have less useful work. So as we have energy that's degrading in quality, we necessarily have a production of entropy. So as we go from high energy to low energy, some entropy is generated in the process. And a real process will always occur in the direction of increasing entropy. So a hot body will always cool down. So we have a net entropy increase as that process occurs. If we look at property diagrams, we can see in visual format the quantity of entropy that is created. So on a TS diagram, if we're plotting temperature and entropy, this area under the curve is equal to the reversible heat transfer. And this is analogous to the work on a PV diagram. So if you remember on a PV diagram, the area under the curve is equal to the network output or the boundary work output. The same goes for this TS diagram, that we can show that it's equal to the reversible work. Similarly, on a Mollier diagram, if we want to look visually at how much entropy change happens for a given work input or output, we can have another idea, and we can compare systems and cycles one to another by seeing how much the entropy increases and how much usable work we're able to receive from our system, or in some cases how much work we have to put into our system and then how much the entropy increases. So this gives us an idea of the magnitude of the irreversibilities in our process. So entropy is always increasing because there's always some entropy created or generated during an irreversible process. And this is not a property of the system necessarily, it's the property of the process. So we can exact change upon a system through a multitude of different processes. However, we in engineering design like to choose a process that results in the least amount of entropy generation. So in other words, we want to minimize irreversibilities and become or perform a process that's as close to reversible as possible. So we see these terms here in this equation, that the change in the entropy of the system is equal to the entropy at the beginning minus the entropy at the end. And then we can set this equal to this other side of the equation from the Clausius inequality, that it's the integral of the reversible heat transfer from state 1 to state 2 plus this entropy generation. And in the case of an isolated system where there's it's an adiabatic system, there's no heat transfer, then the entropy generation of this system is going to be equal to the change in entropy of that isolated system. And that will always be greater than 0 for the irreversible case, and it will be equal to 0 for the reversible case. So this isolated system can also be identified as a system plus its surroundings. So it's not just adiabatic systems, but if we expand the system to include its surroundings, then it becomes adiabatic or isolated as well. And again, the entropy generated is always greater than or equal to 0. And we can actually consider the universe to be an isolated system, so the entropy of the universe is always increasing. So in summary, for a reversible process, the change in entropy is equal to this integral of the change in heat transfer over the temperature, and this is for a closed system. But for an irreversible process, we'll have this integral of the del Q over T plus whatever entropy is generated by the process itself. And then again, as we expand out to an isolated system, we can see that the total entropy change is equal to the entropy generated, which is also equal to the entropy change of the system plus the entropy change of the surroundings. And in the case of a reversible system, it's equal to 0. Any other system, that has to be a positive quantity. When we're looking at pure substances, we can simply look up the entropy change in the property tables. So it's a property, it's fixed at any given state, and the entropy relations in terms of other property values are available. They've been tabulated, and it uses the set reference point, generally absolute 0. So we look at them up the exact same way we do any other property. You know, if it's in the saturated mixture region, we need to know the quality, so the entropy is equal to S sub F plus X S sub G. If it's a compressed liquid, then we just make the compressed liquid approximation where the entropy at some temperature and pressure can be assumed to be the saturated liquid state at that temperature. So that's the approximation when we're dealing with liquids that are below the dome or to the left side of the dome. And then for a superheated vapor, we just simply look up the entropy at two different, at two independent property values, so temperature and pressure, temperature specific volume, whatever two independent intensive properties we have. I mentioned before that there are some relations that relate entropy to other property values, and two of the more famous ones are called the Gibbs Equations. So there's the first and the second Gibbs Equations, and if you want to know the derivation of those, you can look back in chapter 7. I don't feel like we need to cover that again, but these equations are valid for simple compressible systems undergoing a change of state. So it can be an open system or a closed system, and it can be a reversible or an irreversible process. So these are very handy to us because we can calculate this entropy change using other property values. So let's look at a couple of specific examples. One is that we can calculate the entropy change of liquids and solids. So if it's a truly incompressible substance, then the entropy change depends on temperature only. Because if we look back to these equations, if it's a compressible substance, then this change in specific volume goes to 0. So we can say that the ds is equal to du over t. So this part of the equation goes to 0. And we can rewrite du in terms of C sub P or C sub V. For an incompressible substance, C is the same, so C sub P or C sub V are the same. Which means that if we calculate this integral of du over t, we get C times the natural log of T2 over T1. And in the special case of an isentropic process, so there's no entropy change in this particular system, meaning it's a reversible adiabatic process, or there's some other reason that it's isentropic, then this S2 is equal to S1, so this equation goes to 0. And in order for that, that relationship to be satisfied, T2 over T1 has to be equal to 1. So the natural log of 1 is 0, which means that T2 has to be equal to T1. So any isentropic process for an incompressible substance has to also be isothermal. So again, that's a special case. It's not applicable for every process, but if it is undergoing an isentropic process, then it will also be an isothermal process for liquids and solids. And when we're talking about liquids and solids, we're talking about truly incompressible liquids, not like a saturated liquid. We can also look at the entropy change of ideal gases. So starting again with the first and second Gibbs equations, we can substitute in some of the relations derived from the ideal gas equation. So we know that du is equal to C sub v dt, and that pressure is equal to RT over V. So if we substitute these things into this first Gibbs equation, it then reduces down to something that's in terms of property values only. We can also, well, I guess C sub V might or might not be a function of temperature. And then the second Gibbs equation, we perform a similar analysis, so we can reduce it down to here. So then if we take the integral of both sides, we find S2 minus S1 is equal to the integral of C sub V as a function of temperature dt over T plus R natural log of V2 over V1, or in terms of pressure instead of specific volume. So the two Gibbs equations are equivalent. You can use them at any point for any process. However, you may find you want to use the first equation over the second or the second over the first, because maybe instead of knowing pressure, you know specific volume at the initial and final state, or you don't know specific volume, but you do know pressure. So depending on what information you're given about your problem, you might use the first Gibbs equation, or you might use the second Gibbs equation. So using the Gibbs equations, we can perform two different types of analysis. We can do an approximate analysis. So instead of knowing this functional relationship between C sub V and temperature and then integrating, which can be complicated and in many cases requires a numerical approach or some other approach, which we'll talk about in a minute. Instead of doing that, we can say, well, I don't know C sub V as a function of temperature, but if I know my initial and my final temperature, then I can say, well, I'm just going to assume it's a linear relationship and that C sub V plus at the initial and final state over 2 will give me some average C sub V for the total process. Okay, so you can either do it that way where you can average the two C sub V values at the initial and the final state, or you can evaluate C sub V at some intermediate temperature halfway between the temperatures in the process. And then the same for the second Gibbs equation, that you can analyze it in a similar manner where you find the average C sub P and evaluate it at an average temperature. So that gives us a pretty good estimation. But if we want to know the exact values for the change in entropy, then we need to use this exact analysis. So the functional relationship, like I said, is a somewhat complicated equation, but it is known, and it's already been tabulated using absolute zero as a reference. So rather than tabulating entropy, which is a function of temperature and pressure for an ideal gas, they've tabulated this functional relationship, which is based on this integral here. So this C sub P, the integral of C sub P is a function of temperature times dt over T. So this has been calculated for every value that's given in the table, and we can look up these reference entropies in order to allow us to solve this portion of the integral. So if you remember, this section of the integral is now being replaced by this little term it's called a reference entropy. So it's a function of temperature only, but the total entropy is a function of temperature, pressure, and specific volume. So we can replace this part that's just a function of temperature only, or we can input it into the equation, but we still have this functional relationship here. Okay, so we can use these values from the table and then add in this little correction factor, which allows us to see how that entropy is changing with pressure. And you can see that if it were, for example, an isobaric process, meaning P2 is equal to P1, that this term would go to 0. So there would be no, if there's no change in pressure, then it would just be also, it would necessarily also be an isothermal process. So this S2 minus S1, the reference entropy, would be equivalent to the actual change in entropy. That's just in the special case where there's no pressure change as well for that ideal gas. So let's do another example. If we have air that's expanded from 1500 kilopascals and 400 degrees Celsius to 200 kilopascals and 45 degrees Celsius, we want to determine the change in the specific entropy using both methods. First, using constant specific heats, and then using the exact analysis. So we're not really told anything about the process, just that the air is expanded. It might be a piston cylinder device. It might be through some sort of a nozzle or a turbine. We don't know. Or a diffuser, I guess it would be, not a nozzle. So we just do this little picture like this, which allows us to know and understand that it's being expanded, and as it's expanded, the pressure and temperature decrease. We don't necessarily know the process. But in this case, it's not important to know the process because the end results will tell us how our entropy has changed during that process. So let's look at it in the two different ways. So again, we make our approximated little picture. I've converted from Celsius to Kelvin, so 400 Celsius is 673 Kelvin, and 45 Celsius is 318 Kelvin. I've also gone ahead and looked up in the property tables for air my R value, which is 0.2870 kilojoules per kilogram Kelvin. And then I know that I'm going to need a C sub P value, which I can find two different ways. One, I can find the intermediate temperature and look up C sub P at that intermediate temperature, or I could look up C sub P at each of these two temperatures and find the average. I opted to do it by using the temperature because then I only have to interpolate on the table once. So at 495 K, it's close to 500 Kelvin, not quite. So by interpolation, I can find that my C sub P value is 1.028 kilojoules per kilogram Kelvin. So again, I'm working in Kelvin because it's the absolute temperature scale, and for these types of problems, it's necessary to work in Kelvin. Okay, so starting off with the constant specific heat analysis, I know from the equation that delta S is equal to C sub P average times the natural log of T2 over T1 minus R natural log of P2 over P1. And in this case, I chose to use the second Gibbs equation because I was given an initial and a final pressure, initial and final temperature. So I had all the information I needed to calculate that. I just had to look up a C sub P and an R value. So if I plug in the numbers for that, 1.028 times natural log of 318 over 673 Kelvin, minus this R value for air, which is a constant, 0.2870 kilojoules per kilogram Kelvin, times the natural log of 200 over 1500 kilopascals. So I find my delta S value is equal to a negative 0.1924 kilojoules per kilogram Kelvin. Okay, so that brings up the question, well, how can I have a negative entropy? Think about that for a minute. Well, the answer is yes, your entropy can decrease. That's fine. That does not violate the second law of thermodynamics. It doesn't violate the increase of entropy principle because we're just looking at the system. So our system goes from one state to another state and the entropy happens to decrease. However, if we were to look at the effect on the surroundings, we would find that the entropy of the surroundings increases by an amount equal to or greater than this value. So in the special case that the the entropy increases by the same amount as this one decreases, then it would be a reversible process. But more likely is that it's an irreversible process. So we would find a delta S that is a greater value in the positive direction of entropy increase. Okay, so if we want to perform the exact analysis, then we go to the tables. So table A17 is the table for ideal gas, air as an ideal gas, and we can look up these reference entropies. So at 673 Kelvin, we find a reference entropy of 2.5306 kilojoules per kilogram Kelvin. And at 318 Kelvin, we find this other reference entropy at 1.7606 kilojoules per kilogram Kelvin. Okay, so we've looked up those reference entropies. All that's left is to plug those into our equation. So rather than calculating it as we did here, we'll plug it into the equation using the exact values. And we get an answer of negative 0.1917 kilojoules per kilogram Kelvin. So as you can see, these values are fairly close. And in fact, I calculated the percent error to be equal to 0.365%. So for a short range temperature increase or decrease or over a linear interval, using the approximate analysis is probably fine. It doesn't result in a significant amount of error. However, if you have the tools and the ability to calculate using the exact analysis, you will get a more accurate answer, which will have fewer errors that are propagated along it. You know, if you're doing an analysis that involves many different components of the system, you know, that maybe your total entropy change for each component might be very close to the exact analysis, but over time or over several different iterations of these calculations for different devices, then your errors start to add up. So you'll have additional error in your total entropy change. Okay, so let's talk about reversible steady flow work. So again, if we're looking at our system and we want to know what the reversible work of that system is for an open system, we can say that the reversible work is equal to this integral of negative VdP minus the change in kinetic energy minus the change in the potential energy. So in this case, this VdP is the flow work that is done as our fluid moves through our system. And we talked about this again previously in chapter 6 and 7. So if we assume incompressible flow, meaning that our specific volume does not change, it can come outside the integral, and the integral of dP is just P2 minus P1. So we have this negative sign here, negative specific volume times the pressure change to inform us of this work that's being done on the system. So as our pressure increases from P1 to P2, then that means that we are doing work to the system, and if our pressure decreases, then work is being done by the system, so it would end up being a positive number. So this negative sign is necessary so that the signs work out. In the case of a device that involves no work, if we set that equation equal to 0, then we get something that looks like this, which for those of you in fluid mechanics might recognize it as very similar to the Bernoulli equation. An isentropic process is one in which the entropy does not change. So the change in entropy is 0, meaning that the entropy at the initial and the final states are the same. Actual engineering devices are sometimes adiabatic, and they can be approximated as reversible if we minimize friction and other losses. So the isentropic assumption allows us to, again, look at the best case scenario. So similar to using the Carnot cycle to evaluate a heat engine, this allows us to look at it in a way that we've minimized irreversibilities, and we're looking at it as a system which looks, for all intents and purposes, as if there is no entropy generation. So a reversible adiabatic process can always be said to be isentropic But an isentropic process isn't always reversible and adiabatic, because you can have an irreversible process in which you also have heat transfer, but the change in entropy is balanced out. So in some cases, if we're adding heat to our system, that can make up for the fact that it's not a reversible system. So we can look at the individual steady flow devices. The isentropic efficiency of a turbine is equal to the ratio of the actual work divided by the work that would be done if that turbine was isentropic. So if we look at an HS diagram, so again, this is the Mollier diagram, which allows us to look at reversibility for work input, we can see that in the isentropic case, we maximize our work output, whereas in the actual case, because our exit pressure is for the same exit pressure, we actually get a slightly lower value of enthalpy on this diagram, and we increase the amount of entropy that we generate during the process. So you can see that the best case scenario would be the isentropic process, and we can calculate the isentropic efficiency by just dividing the actual work, which for a turbine would be H1 minus H2 actual, so this actual enthalpy, and then we divide through by H1 minus H2 isentropic. So we would need to determine both the isentropic case and the actual case in order to calculate the efficiency. Sometimes our efficiency is given to us in the problem, so instead of calculating the efficiency, we use the efficiency maybe to calculate the enthalpy at the final state. So if we know the initial state and we're given some information about the final state, and we assume that the entropy doesn't change, we could find H2S, and then if we knew the efficiency, we could solve for H2A. Similarly, for pumps, we have the isentropic pump work divided by the actual pump work, and the work for a pump, because it's pumping a presumably incompressible fluid, can just be replaced by V times P2 minus P1, and then the actual work for a pump. So this is the isentropic case. The actual work for the pump would be H2 actual minus H1. So again, we see that in the case of the isentropic device, we have a minimal work input, whereas in the case of the actual device, we have a greater work input required. So that should make sense to you physically, that if our device is not reversible, then we have to actually put more work into it in order to achieve the same pressure drop, or pressure increase, I guess, in the case of a pump. The same for a nozzle, that we can look at the actual kinetic energy at the exit divided by the isentropic kinetic energy. So if it's a very small inlet velocity, then we can assume that V1 is approximately equal to 0. We can say that H1 is equal to the actual enthalpy plus V2 squared over 2. And if we don't know information about the velocities, then we can again use the enthalpies by looking them up based on the temperature and pressure of our system at those given points. So again, we look at the actual case, we look at the isentropic case. And for the same exit pressure, we can see that the velocity in the isentropic case will be greater than that in the actual case, meaning that there's a greater kinetic energy available at the outlet. So we've lost less energy, or in other words, there are fewer irreversibilities. So as compared to the actual case, we have a greater kinetic energy. Compressors are just a little bit different, because we can look at the isentropic case of the compressor in a very similar fashion as to what we have done for the turbine and the pump and the nozzle, but we can also do a little bit more. So when we look at a compressor, the ratio of the work is the isentropic over the actual, and again, we can look at this H2S minus H1 over H2A minus H1. So on the diagram, of course, this actual compressor work is greater than the isentropic compressor work. Okay, that makes sense. It's a work-consuming device, so we have a greater work input required to get the same exit pressure. However, we can do some things to our compressor that will allow us to have a smaller work input. So in some cases, we can make the compressor isothermal, which means that we look at the isothermal compressor work divided by the actual compressor work. And so although the isentropic case is really, really good, what we want to actually do is move this dot further and further and further down this line. So we can do better than the isentropic case by cooling the gas as it's being compressed. And if we cool it so much that it's an isothermal process, we have our best case scenario. But we're going to look at some of the intermediate processes as well. So with an isentropic process, there's no cooling. We can calculate the work to the compressor using this equation where K is the ratio of C sub P and C sub V. That can be looked up in a table. So table A3 in the back of the book for an ideal gas. So making it also clear that this is compressing ideal gases. This is not necessarily compressing steam. So in the isentropic case, we have this equation. In the polytropic case, that means that we're providing some cooling. We have this equation, and then in the isothermal case, it's the maximum amount of cooling. So the idea behind cooling this gas as it goes through the compressor is we want to keep our specific volume smaller. And by keeping the specific volume smaller, we're minimizing the amount of flow work that needs to be done as we move that fluid through the system. We can also use multi-stage compression, which is actually what the way that it's done more often in actual industry, because cooling a gas while it's being compressed is not really feasible or practical in many cases. So sometimes we compress it to an intermediate stage, cool the gas back down, and then compress it again. So we can minimize the work when we compress it to an intermediate stage where that intermediate pressure is calculated as the square root of P1 times P2. And that's not exactly halfway in between the two pressures. It's at some intermediate pressure. So you can see how even though we want to minimize irreversibilities in our systems, that sometimes there are things we can do to actually decrease a work input or increase a work output simply by changing the way that we run our working fluid through the system. So in the case of a compressor, by cooling it, minimizing the specific volume, we decrease our flow work, which then decreases the amount of work we have to put in to compress that gas. However, sometimes we have to balance cost. So it may cost more to implement this multi-stage compression than any savings that you gain, or maybe the payback period is such a long time that you'll have to replace this system before you ever pay it off. So those are all the considerations that need to be accounted for as we look at implementing these types of changes to our steady flow devices. Okay, so this leads us all to our final discussion of entropy balance. So we've looked at different systems. We've looked at how we can look entropy up in the property tables. We've looked at isentropic systems and how we can compare them to actual systems and find the isentropic efficiencies. But we can also perform an entropy balance, which is analogous or somewhat similar to an energy balance. However, there are some very distinct differences in that entropy is not a conserved property. Okay, so the entropy entering the system minus the entropy leaving the system plus this entropy generation term is equal to the total change in entropy of the system. So this entropy generation term is what makes it such that we always have this, this increase of entropy as we undergo a specific process. Okay, so again, the entropy of the system can decrease, but this entropy generation term will always be positive. So even if we have, you know, a net negative entropy change of our system, we'll have generated entropy during that process. So it will satisfy the increase of entropy principle. And that entropy generation is often reflected in a net increase in entropy in the surroundings. So we can look at it in the general form where if we divide through by mass, then it's just the entropy in minus the entropy out plus the entropy generated is equal to the entropy of the system, entropy change of the system. We can also look at it in the rate form. So if we put our dots above all of these individual terms, then it's a change in entropy with time, and we can look at it that way. So for a reversible process, this entropy generation term goes away, and the change in entropy is just equal to the change in entropy of the system without generating any entropy, because it is the irreversible processes that generate entropy, not the reversible process. So you can still have an entropy change for a reversible process. You just won't have created additional entropy and put it out there into the environment. So understanding and recognizing entropy for what it is and how it comes into play in these equations is important. Okay, so for a closed system, we can look at it a little bit more carefully, that we don't have mass flow in and out of our system, so the entropy can only be transferred to and from the system via heat. There is no entropy that is transferred via work. It's transferred via heat. So we can have the sum of all of these individual components of heat divided by the temperature at which that heat transfer occurs, and we use the temperature of the boundary for that. If the boundary is at different temperature, many different places around our system, then we have to add up all those individual pieces or components of heat transfer at their individual temperatures. If the process happens to be adiabatic, or the system is adiabatic, then the entropy generation is equal to the entropy change of the system. And note that this will always be a positive quantity or zero. So if there's no heat transfer, meaning we're not removing heat from the system, we're not adding heat to the system, then the entropy generation is always going to be positive. Or in the off chance that it's a reversible process, then it would be zero. But a reversible adiabatic closed system doesn't often have many interesting things to study. So take that for what it is. And then if you're looking at a system plus its surroundings, so again, this gives us an isolated system, then the entropy generation is equal to change in entropy of the system plus the change in entropy of the surroundings. So it's a similar analysis to an adiabatic system, in that we've expanded our system so large out to the surroundings that we've taken into account all of any heat transfer that occurs, that there's no longer heat transfer occurring at the boundaries of the system. We've made everything be one big system. We can also look at entropy balance for an open system. And so in this case, we now have the potential to have heat transfer or mass flow across the boundaries of the system. So this mass carries entropy with it, because if it's a substance that has some set entropy value that's greater than what's already in the system, then it will serve to increase the entropy value of the system. Similarly, as mass is exiting the system, it takes some of that entropy with it. If it happens to be a steady flow system, then we can set this side of the equation equal to 0. So the entropy of the control volume is not changing with time. It's a consistent value. So the change in entropy of the whole control volume with time is set to 0. And then we just have energy coming in and out due to heat transfer and mass flow. But that's all balancing itself, so it's not changing over time. And then if it happens to be steady flow single stream, these summation terms go away, that we have one consistent constant flow rate, mass flow rate, multiplied by this entropy at the inlet minus the entropy at the outlet. And if it's steady flow single stream adiabatic, then it reduces even further. We get rid of this heat transfer term so that we just have the mass flow multiplied by these entropy terms plus this S dot gen is equal to 0. So we could say this S dot gen will just be equal to the mass flow of the entropy entering and exiting the system. So let's do another example. In this case, we have a turbine, and we have steam at 6 megapascals and 400 Celsius entering an adiabatic turbine at a rate of 15 kilograms per second and leaving at 100 kilopascals. So it's entering 6 megapascals, 400 Celsius, and it leaves at 100 kilopascals. And it's a steady flow, single stream, so the mass flow rate is consistent at 15 kilograms per second. If the isentropic efficiency is 75%, determine A, the temperature of the working fluid at the outlet, and B, the rate of entropy generation during this process. Okay, so to find the rate of entropy generation, we will need to perform an entropy balance. So let's look at this example. To set it up, again, we draw our simplified picture, 6 megapascals and 400 Celsius coming into the turbine, 100 kilopascals leaving. We don't know the network output, but we do know that it's 75% efficient according to isentropic efficiency standards. So in order to find the temperature at the outlet, we need to either somehow find some other property value that allows us to look it up or calculate it. And in this case, we know that the outlet is at 100 kilopascals, but we don't know any other property value, so we're going to have to figure that out. We do, however, remember that isentropic efficiency is equal to H1 minus H2 actual over H1 minus H2 isentropic. So we can look up the H value for the isentropic case, and we'll be able to use that to calculate this H2 actual. So there's a little bit of a process to do that, but bear with me and we'll find it. So let's first go to the tables. So in the initial case, we have a superheated vapor, so I believe that's table A5 or A6. I don't have my book in front of me, but it's the superheated vapor table for water. And we have a pressure of 6 megapascals, a temperature of 400 Celsius. So we can look up the other property values. So we look up our entropy, which is 6.5432, and our enthalpy, which is 3178.3, and the associated units with those. So if we want to know our isentropic state, we can say, okay, we know our pressure is going to remain the same, and that our entropy is going to be equal to the entropy at the initial state. So we can just set that S1 is equal to S2S. So subscript S means it's the isentropic state. It's the imaginary state. And then we calculate our quality based on that. So we find that S is equal to 6.5432. Calculate the quality is going to be this S value minus the S at the fluid state divided by S sub Fg. And I think I forgot to erase something there. Okay, just ignore that part. So if I plug in the numbers for that, looking them up from the table, again, table in the back of the book, superheated for a saturated liquid vapor mixture, because when I looked on the table, this 6.5432 was in between S sub F and S sub G at 100 kilopascals. So I calculate my my quality to be equal to 0.8653. So we have a saturated liquid vapor mixture that's getting closer and closer to the liquid state. Using that, I can calculate my H2S. So H2S is equal to H sub F plus X HFG. Plugging in the numbers for that, again, getting H sub F and HFG from the table, then I find that my H2S is equal to 2370.92. So going back to this equation, I can plug that in. So I know H1, I looked it up at state 1. I know H2S, I looked it up and calculated it based on the quality. So I can solve for H2A. And so if I rearrange, plug in the numbers, I find that H2 actual is equal to 2572.77 kilojoules per kilogram. I should have had units on that. Okay, 2572.77. I'll add units in my document. So at 100 kilopascals, again, this 2572.77 is in between H sub F and H sub G, so it's still a saturated liquid vapor mixture, which means that our temperature is just the saturation temperature at that point, or 99.61 degrees Celsius. Okay, so now we have this H2 actual. We go back and we figure out some of the other properties at H2 because we want to know the entropy generation. And if we perform our entropy balance, we know that we're going to have an entropy of the initial and the final state. So again, P2 is 100 kilopascals, T2 is 99.61 degrees Celsius, or the saturation temperature. And then now we know H2, which is 2572.77. So that gives us our second independent intensive property, because pressure and temperature are not independent of one another, but temperature and H, or pressure and H, are independent. Using H, we calculate the quality at x2, so H minus H sub f over H of G, again looking up those values from the table, we find that x2 is equal to 0.955. Using that, we calculate our entropy. So our entropy is equal to S sub f plus x S of G, which is 7.091 kilojoules per kilogram Kelvin. So if we perform our entropy balance, we start with the general form of the equation for a steady flow device. We know that it's adiabatic, so this Q dot K over TK goes to 0 because there's no heat transfer. We also know, because it's steady flow or steady state, that this ds dt goes to 0. So we're left with this m dot s in minus m dot s out plus s dot gen is equal to 0. And because we have just a single stream steady flow, our mass flow rate does not change. And that was given to us initially in the problem as 15 kilograms per second. So s dot gen is equal to m dot times s2 minus s1. So if we plug in the numbers for that, 15 kilograms per second times 7.091 minus 6.5432 kilojoules per kilogram Kelvin. Kilograms cancel out, so we are left with kilojoules per second times Kelvin, which a kilojoule per second is just a kilowatt. So our final answer for S dot gen is 8.217 kilowatts per Kelvin. That is the end of the lecture for today. I'll move it back onto this screen in case you're still copying things down. Please be sure to go to Blackboard, look up the homework assignment for this lecture, make sure that you get started on that. If you have any questions, I should be available by email. I'll be in a very different time zone, so don't wait till the last minute to email me. Earlier in the week would be better. If you wait until Monday night, chances are I probably will not receive that email as I will be returning to the U.S. So get started on it. Please use or refer to notes and homework from last semester if you're still confused about entropy. It's hard to try to cram that all into one lecture, but I'm presuming that you have already a foundation or basis for understanding. So let's carry on with that. And again, come see me in my office hours next week, or send me an email if you still have questions. Thank you.